Good evening all, welcome back to basic coding on the C64, and this time we're going to finish off the sound and music chapter, hopefully. And if we do finish this chapter, which I'm not overly confident that we will, but if we do, then this might be the last video of this series. And looking at how many chapters, how many pages I've got left to explain walkthrough, I'm not so sure. But anyway, we start off where we left off, which was that last time we were doing a little playing around with the gain, sustain, decay, attack and decay and all that sort of stuff, pushing that through. So, and we ended up with this program, but since then I have tweaked it a little bit. So if I run this, if I press a key, I got it to say use noise instead. And stop. So basically, alright, yeah, I got to look at. This is a little bit tricky. I changed the waveform, which was, where is it? Down here to 129. That made it noise and active. If I made it 128, it wouldn't be active. It would just be turned off, which is what this 16 does. In the original program, this one here was 17. This one's 16. When they just took away the 1, it just means the on-off bit was not there. Now, I'm not going to go through all the binary to flag stuff again, because I've done it like pretty much every video so far. But in any case, let's continue on with the text and with this. So, at this point, this is the program up the top here. Then I'm going to try to read all this through here, and well, let's see what we get, shall we? Let's go back to this. Okay, run the program a few times and try attacking the attack and decay settings on 930. Yeah, I think I did that. Like, yeah, I did. Like 30 poke, 54277, comma 190, which I already did. Program again, you notice the difference in note. Try other combinations of attack and decay settings to get an idea how you could use different attack decay rates to create a variety of sound effects. Sustain release setting, like attack decay, sustain release share a byte. But remember that this sharing doesn't mean that sustain and release are alike. Sustain is a level, while release, attack, and decay are rates. Sustain is a proportion of maximum volume. You can sustain or hold notes and sounds at any of 16 volume levels. This table shows you what numbers to poke for sustain release values. So hold on, I'll show you this table, which is there. Okay, you all see that? Good. So let's get back. So high sustain is 128, medium sustain is 64, low sustain 32, lowest sustain 16, high release 8, mid release 4, low release 2, lowest release 1. Note you can increase the sustain level by adding together all the sustained values, i.e. 128 plus 64 plus 32 plus 16 equals 240, which is the maximum sustain level. A sustain level of 128 is approximately 50% of volume. You can increase the release rate by adding together the release values 8, 4, 2, and 1, which equals 15. This is the maximum release rate. Combine the sustain level and release rate the same way you combine attack and decay rates. Add the two values and poke the total to the memory location of the voice you want. To see the effects of the sustain level, adding sustain level setting, add this line to the last sample program, which I think I did. Line 35, yes. 35 poke. 54278. Well, I'm going to make that a lot bigger. Let's try changing this. Whoops, wrong thing. Wrong window. Alright, this one. Let's go to list. Let's get that program back. So 35. Let's go change that to not 128. Let's put it at the maximum sustain, which was 240. So if we go 240, enter. Now let's go back down here and run. Sounds exactly the same. Maybe the sustain doesn't work on a noise waveform. So if I change this back to 17, let's see what I get. Shit, I hate doing this. 17. Close enough. That will work. Let's do it this way. So let's go back down. Let's run it. Press a key. Doesn't do anything. Oops. Okay, well anyway, now run the program and note the change. With line 35, we tell the computer to sustain the note at high sustain level. You can vary the duration of a note by changing the count in line 70. Remember that the sustain level maintains a note at a proportion of the volume the note falls from its peak volume. This isn't the same as the note's duration. I see. So so line 70 is this one. Let's change U to say 600. That should make it run a bit longer. Press key. Alright. We'll leave it at that. Okay. To see the effect of release rate, try changing line 35 to poke 54278 89. Sustain 80, release 9. So where is it? It was up here, was it? So we go 89. So let's run this again and see what we get. That sounds really cool. That sounds good. That sounds really good. Cool. Next page. So. Alright. So we've got on to a new chapter. It's called Sample Sound Program. This brief sound program summarizes what you have learned so far about making music on your C64. Choose the voices. Okay, so first off, choose the voices you want to use. Recall that each voice uses different memory locations into which you'll poke values for waveform, attack rate, etc. You can play 1, 2, or 3 voice together, but this program only uses voice 1. So you clear the SID chip, set the volume, set the attack and decay, you set the sustain release, find notes you want to play in the table of musical notes and appendix M and enter the high frequency and low frequency values for that note. Each note requires 2 pokes. Alright, start waveform. Here it's a triangle. Enter a timing loop to be between notes. We use 250 for a quarter note. Stop note by turning off chosen waveform. Here is a longer program that demonstrates your C64's music making abilities. Alright. Well. Okay, so let's go. So, go over there. Move my teapot over. So let's get a typing, I guess. So 5. In case you're wondering, hold on, I'll bring it back up. Me. So this is all I just read out. It's just this little program here. So basically we've got to set up all the notes, like all the attack, decay, what the voices we're going to use and all that, what notes we're going to use, and then this is the actual notes we're going to use. Okay, so it's going to play through this loop here to play all the notes, and once it gets to data -1, as you can see up here, it just ends the program. Okay, so let's get on with it, shall we? Because this is going to be a long one. Oh Jesus, bloody hot a bit. Alright. No drink. Alright, so 5. Remark. Musical scale. 7. 4L equals 542 722 542 96 poke L with 0. So essentially this is what this line clears out all the SID registers. So make sure there's no leftover data in there that could alter things. Yeah, I got that right. Cool. 10. We set the volume, so we go poke 54296 15, and that is the volume for all of it, I think. Hold on, let me have a quick double check. Way back here. Controls and filters. Yeah, so that's full on. That's the volume for all the voices. And I don't think you can control the volume for each of the other ones. So you have to adjust your frequency and height and whatnot. Sustain. That's how you adjust your volume for each individual voice, I'd imagine. Okay. Just move that back a bit. Just to make it a little bit neater. 20. Poke. What are we doing here? We're setting the ADSR. So basically the attack, decay, sustain, and release. Yeah. Poke. 54277. 7. I remember having controls like this on my organ I used to play way back, and the one I pretty much learnt on. And it had huge these sliders for attack, decay, and sustain and release and all this, and I used to love playing with those sliders. Playing with different notes, making them really moody sort of thing. 2, 7, 8. 1 through 3. So that, okay, so we've got attack and decay going on there. So the 277 is the attack, decay, and 278 is the sustain and release. Okay, so 30. This, oh, was it 30? No, it's 50. 50. So reading our data into A. 55. If A equals -1, then end. So basically that's how you control when them stop reading, stop start reading, stop reading, stuff like that. Okay, so this reads first number from line 110, which is 16, 95, 18, 2. So those are the high and low values. I still don't understand. Not sure. Oh, hang on. That's right. Read is a loop. So you read one value. So when it does it, it reads the next value. Boop, 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 boop. So you go read, 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 read. Dot, 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 dot. Okay, so it reads one value at a time. I think. Yeah, that's what it does. Yeah. And so 60. Read B. So now we'll read the next value in the data. Go ET poke 54. So since we've read the data, now we've got to poke it into memory. 54273. That's the thing about, remember when you're coding these old machines, is that everything is in memory. So you reference your things, you get things happening by poking, just, poking addresses. Essentially poking it with a big stick and see what happens. 54272 with B. So setting the high and low frequencies of the note. And I'll show you what that means in a minute. Hold on, I'll show you right now actually. Where does it say it? Doesn't actually have any visual description of what the high and low frequencies are. So basically, hold on, I'll show you something. Turn me back on. Not that one, that one. So basically we've got our waveforms here. So the frequency up here is your high frequency. Frequency down here is your low frequency. So you can offset them somewhat. I think that's what it is. I'm not exactly sure, but I think that's what it is. But anyway, way back in the appendices, no, that's the screen. No, that's not the. No, that's not the appendices. That's the. Here we are. Look, here's all our musical notes. There's a couple pages of these, but basically, this is what you have to put in your high frequency. That one, a high frequency one on it, and a low frequency, and basically how many cycles that note will take. It'll chew up. But anyway, I've got to go back to where I was now. Oops. Yeah, here we are. Oh, it's getting hot in here for some reason. That's why, because I closed the bloody window. Because I didn't want this to be very noisy and have all the background noise. So, sorry. Alright, where are we? B. So basically this line here just pokes the values that we get reading into memory. Then we turn the note on. So we go 85. We turn the voice on and say use this waveform, which in this case is a sawtooth, if I remember correctly, or triangle. Gives a nice little Chinese sort of sound to it. So what is it? 54276. There's a lot of values to remember, isn't there? Thankfully, a lot of people would have just noted them. Like they write them down, like they would have a notepad saying what's what, so to speak. So let's play some notes. So let's play the note. So the note is now playing at this line, at line 85. It is now starting. You should now hear something. And we're going to keep it going so we'll go 4 T equals 1 to 250. Then next, just loop itself, so just causes a little bit of delay. Then we turn it off. So it does it for 250 milliseconds, I would say. Judging by my experience I did earlier today with that other program, it takes about, one cycle is about 1 millisecond. 5, 4, 2, 7, 6, 16. Now that 16 means it is sawtooth or triangle, but it's turned off. The gate bit is turned off, which is essentially the very first bit of that number. Then we go, once again, just to let it release out. So I go 95. 4t equals 1 to 50. I do have to admit, this manual is pretty thorough. It's not too bad, I have to admit. Some things have been wrong, which we had to fix along the way, which is understandable. And so we loop the program over again to go again, to get the next note. And that's what we're going to do. No, it is 100. It's so weird seeing it go to 20 and go to on anything else than a 10, but I've done that too much. Okay, 110. Data, let's put in this. Here we go, 16. So that's the low frequency, that's the low frequency. Then 195 for the high. 18 for the low. 209 for the high. 21 for the low. And 31 for the high. 22 for the low. 96 for the high. New line, 120. Data, 25 for the low, 30 for the high, 28 for the low, 49 for the high, 31 for the low, 165 for the high, 33 for the low, 135 for the high. Then right at the end here, 999, so nothing can possibly be after that. And we go data, -1. That means if you read at, hold on, where are we? If we read this line here, if the value is -1, then just end the program. So once it's gone, end. And it doesn't loop itself back again. Okay, so to read Alright, so let's run it. First list, just to make sure I got it all right. Yep. Read if A equals that. Alright, yep. So let's run it. Not bad. Not bad at all. So I wonder. Well, first of all, let's change the waveform. So what waveform do we want is a bit tricky. I want to put it on to pulse, is what I would like to do. Pulse. Pulse is bit number 6. So, can't really show you, can I? Well, I don't have the GIMP open to work this out. I got my scientific calculator here. I'll see if I don't think it's going to work, but I'm going to try add a new window capture device. So create new. No, doesn't want to work. God damn it. So let's get rid of that. Yes, get rid of that. Cancel. Get rid of it. Yes. I'll try changing it from here. I don't want to do this, but we'll see. Nope, doesn't want to work. Anyway, I'm just going to work this out. Just give me a moment. Using the GNOME calculator in programming mode, so I can actually work this out myself. So basically, I need the 6th bit. So 0, 0, 1, 0, 0, 0, 0, 1. That is 33. I think I got one too many zeros. Yeah. 1, no. 1, 2, 3, 4, 1, 2, 3. Okay, so it is 33. Okay. So we'll go over here. Let's change up here to this one here to 33 and change this one to 31. And let's put you in. So let's run it. I don't think this will work because a pulse uses something else, but let's try this. It does! That changes it completely differently. So that was a triangle, I think it was. Not that one was pulse, so basically a square wave. I'll actually show you, hold on. Where is it? See, once again, time to look at my ugly mug. Okay, see, that's the pulse. That's what we just looked at. And before, I think it was sawtooth or triangle. Well, anyway, that's what it was the first time. And this is a triangle. How about we try triangle, shall we? Oh, bring this back. What shall we look at? Cells. Okay. Oh no, it was triangle. So we change it to a sawtooth by changing it to. I did change it to 33, so I must have been well off. I think I am. Oh, I am. Whoops. That was this one here. I've already done. I got my binary wrong. That's sawtooth. I want pulse. So we go this again. We go. So we go 0, 1. I forgot everything's 0 index. So 0, 0, 0, 0, 0, 1. 65 is what we want. So yep. Let's change this to 65 and this one down here to 64. And yeah, right at the end here. So let's run it. This may not run because it's pulse, and pulse uses something different. Yeah, pulse uses a pulse width and not a frequency. Let's try this the very last waveform, which is noise. Let's see what we can get for that. Now, noise is 7. So, okay. So 1, 0, 0, 0, 0, 0, 0, 1. 129. So let's go up here. Let's turn it on to 129. 129, and this one down here to 128. And let's run it. That works. Let's run that again. Alright, so sawtooth to that. So let's follow the manual again. So I'm going to have to go this things up again. Now please remember, when you're doing this, if I pressed enter here, it's loading that back into memory. So it loads that line. Doesn't matter whether you type it here. So if I type, say, 60 here, it'll just override 60 that's there. So what do I need to change to 30? 33 and 32 first. So we'll go this, we'll go 33, enter, so it's in memory, and 32 to turn it off after it's done. So let's run this. Gives a bit of a keyboardy feel, doesn't it? You can also change the sound in other ways. For example, you can change the harpsichords-like sound in the previous program to a banjo-like sound by changing the attack decay rate of each note. Excuse me. Do this by changing line 20 to read 3 and 0. So what was it? This one. Very much. 3 and 0. And let's run. That does not sound like a banjo to me. I don't know what they're on about, because that does not sound like a banjo. Alright, well anyway, moving on. This program demonstrates your C64 can sound like a variety of musical instruments. Yay! Alright, what's this? Now, next bit. Playing a song on your 64. Oh dear, this looks like a long one. The next program lets you play a line from a song, Michael Row Your Boat Ashore. This program uses the pulse waveform, which is a variable width rectangular wave. The third and fourth pokes in line 10 define the pulse width for this song. In this song we use a duration count of 125 for an eighth note, 250 for a quarter note and 375 for a dotted quarter note, 500 for a half note and 1000 for a whole note. When you program your own songs, you can increase and decrease these numbers to match your particular tempo or your own musical taste. So, I see. So, okay, let's have a look. Hold on, I'm going to bring this up. I can see what's going on here. So, okay. So what it's saying, here's the program, right? Now you notice these 4s down here. Well, there's a 4, 1 to 50 there, but look above it, it's a 4, 1 to D. So every time it reads some values, it uses that value down here to say how long that note lasts for. So this data down here will be A, the low frequency, the high frequency, and its length of note. How long the note's going to be. So it's like if it's a quarter note, full note, half note, what have you. So you can define what the note is. So it's if it's a quick note, half note, da 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 da. And then it just does a little break thing here for it to release, and there we are. So if it's -1 and, like down here. So first of all, clearing up things, I guess, and this one looks a lot better written. It's using, instead of using the full start numbers, like the last one, like the 54272 or something like that, it just goes, yeah, use this value, then add values to it to get to ones you want, which is very, very nice. So, let's get to writing this thing, shall we? Because this one looks pretty cool, pretty interesting. So, it's going to take a while for me to actually do this, but we'll see. So, first of all, new. Let's clear up the screen a bit and clear up our memory. So what is line 2 clears the SID chip. Let's do that then. So let's clear our memory for the SID. So 2 4 L equals 5 4 2 7 2 2 5 4 2 9 6. That poke that 0 and next. The next. So that clears the memory. So 5 S. So this is basically where the SID chip starts. So 5 4 2 7 2. That's the memory address of the SID chip. Which my video seems to be getting very popular for some reason. A lot of people seem to like that video of mine. Poke S plus 24. Even had a few people comment on it saying thank you very much for it. And I'm going, alright, thank you. Here's the variable S throughout the rest of the program. Da, 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 da. So line 10. So first of all, we are doing the volume register. So I'm making the volume. So this one is this first poke here, which I've messed up. It's supposed to be a plus there, and I silly trying to use a numpad. Why am I trying to use a numpad? So that sets the volume. Then for voice 1, we set the attack in decay rates. So poke S plus 5 with 88. Oh, God damn it. I did it again. I used the numpad. Plus 5, comma 88. The next one we are doing is the pulse width, because it's using the pulse waveform. So it doesn't use frequencies, it uses pulse widths to determine the note. Like you do on in Game Boy and Nintendo Entertainment System and stuff like that. A lot of the early sound chips did that. They use square waves. What's this? So what's this? Plus, there's the 88 one. So 3, 15. There we go. Next one. So that was on that one. Poke. S. It would be nice, wouldn't it, that someone wrote, or if you didn't have to write so much programming at the time like this. But if you did that, then you'll take away a lot of the joy and flexibility of programming. Because if you make things simple, then you lose functionality. That's just the way that there is no way of adding functionality but keeping things simple. That's just a impossibility. So first of all, let's read some values. So 20. Read H. If H equals -1, then end. 30. Read L. So read the next value. So in this case, the first value is 30, 33. Next value is 35. So I'll go back to these pokes. Hold on. This then we did the, what was it? 5 attack and decay. Then this 3 one here is the pulse width. Then this last poke here. Well, there's the poke. Did I miss some? I did. God damn it. 3. Plus 215. Plus, well, I did it again. Plus 2, 15. That will do. Then the 6 plus 89, that's the sustain and release level. Okay. 40. Read D. So it reads the next value, puts it into D. So, okay. So H, high frequency. D, L, low frequency. D, the delay. Simple enough, I guess. 60. Poke, S, plus 1, put in the high frequency. Then we poke S, but put, which is the very start, and put in our low frequency. Why is he doing it high and low? Then you go, never mind. Then I don't know. What do we do after this? And we'll go poke S plus 4, 65. What's it? So, okay, read the lines, da 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 da. First value assigned until da da da. That's the high frequency, the low frequency. And then, oh, so that sets the waveform. 65 turns it into a pulse. Right, sure. Now I understand. So as we looping through, we could potentially add this to data, add another third read up here in the 50, and put that into there. So in our data below, we could add what the waveform will be for that note. So we can change the waveform on the fly. Might give that a little bit of a shot. There's a bit too much data here for me to do that for every single one. But we'll see. We shall see. So, move the mouse out of the way. And boop. That's 60. 70. That's going on for roughly 40 minutes, I'd say. So 74 T equals 1 to D. So that's our delay. Next. Then we go poke S plus 4, 64. So that turns it off. So it holds it, then now it turns it off. Do a little bit of delay for the next note, which is about 50 milliseconds. So 80, 4, T, 250. And then we just go next. Just do a simple little loop. And then 90. Go to 20. So then it loops itself over and over and over and over until it reaches the -1 in the data, which we are about to do, and then put in all this goddamn data. Oh, this is going to be annoying. But anyway. Okay. Well, first off, line 100. Data 33, 135, 250, 42, 62, 250. Sorry about all this. This is very boring. And yeah. I would like to take this moment, of course, to apologise for taking so long to making this video. I said this last time, I'm very, very sorry now. I'm saying it again right now. Truth be told, I didn't want this to end. I've loved coding on this. I've loved making these videos, and I just didn't want it to end. I was just scared of it ending. But with the recent surge in the views of these videos, it's been, I just felt I just have to do it. I got to stop being a little chicken shit and get this done. And do it the best I can, obviously. I had plans of actually doing this like a live stream or something like that, and I don't know. I don't think it would work because I would have to take questions from people and I'd have to concentrate on the chat or something like that, and therefore I would lose my train of thought of what I was actually doing. Because in this sort of thing, you have to kind of keep your where you are in your program. Like, I just made a mistake just then because I got a little bit distracted. So you're not making mistakes, you're not constantly going back to do things and all that. So I kind of made it a New Year resolution to get these videos, do more videos again. But this time, I'm going to stick to the old school stuff, I think, because they're fun. So I'm not really going to be doing like the city skylines stuff anymore. I might still do a rambling video every now and then. But at this point, I think I should be okay just sticking with the old school stuff. Because people seem to like those the most. Which is cool, I guess. People actually like my videos for one, which is really nice. But anyway. That's all the data put in. That's all our notes and everything. So let's pull a list just to make certain it's all in memory correctly. And I believe it all is. We'll see how we go. So let's run it. So hang on. Okay, so yep. 170 uses a loop to set the duration of the note being played. The value of D is assigned in the read statement in line 40. As you can see, the numbers and data lists are clustered into threes. The first number, e.g. 35, is the high frequency value of the note. The second number, 135, is the low frequency value of the same note. And the third number, 250, sets the duration of that note, e.g. a quarter note. Line A is a timing loop that determines the release time between notes. So essentially how many times, if you're playing a keyboard, it's basically the time difference between hitting the keys. And line 80, yep, okay. Line 90 sends the program back to read the number set for another note. Lines 100 through 120 contain all the data for this song. So let's hear it, shall we? Syntax error in 2. I know what I did wrong. I got a poke. Poke what? L with 0. Next. God damn it. Alright, let's try this one more time. Run. In 10. So let's do this list. Okay, poke S plus 24 is that. Poke S plus 5 is that. Poke S plus 3, that equals that. Poke S plus 2. I see what I did wrong. I missed this here. Because it still thinks it's still one command. Unless that. It says, okay, this is a new command. So let's do that. This is what happens when you're let's see. I'm missing T. T equals what? Equals 1. Oops, I still did it. Equals 1, 2, 50. Next. So we've got one note. And then it's muddled up. So run. And 90. Ah. What's this? What is this? Got to. Got to 20. Go to 20. Okay. Okay, let's do a list. just to make sure. So we've got it all nice and neat. That's our program. That's our data. Let's run it. That's not too bad. Let's try this again. Cool. So let's change that waveform, shall we? Alright, so where did I see that? I see it. It's right there. So you want it to be the sawtooth, which is 37, I believe. No, it's 17 and 16. So we go up here, change this here, this one, to 17, and down here to 16. That way we're not using the waveform one. The pulse wave should sound a bit different. Try this again. Cool. That is really nice. So let's try one more. Let's try this triangle. We've got the sawtooth. Let's try the triangle wave, which is triangle. Triangle is 4, so I need my calculator. So we go 0, 0, 0, 0, 1. Hang on a minute. 0 index, so one more. 1, 0, 1, 3, 4. Yep. So which is 5. 5. Okay. So let's list. Oop, wrong window. List to here. And let's change this to 5 and 4. 5 and to 4. Now let's run it. Okay, I messed up. I really messed up. I totally messed up. So hang on a minute. Okay. Oh, so 5. The 5th one's what I wanted. So 0, 1, 2, 3, 1, 1, 2, 3, 1. And that's 17. Oops. 1. So 9. 9's the one I want. So 9 and 8. Okay. 9. And better presenter to make sure it's in memory. And then this one is 8. Go 8. Okay. Run. Don't work. Doesn't do it. Okay. I think I'm still missing one here. There should be 5. I did. I had it wrong. Again. 17. It's a sawtooth. That's 9. Hang on 1 minute here. That. I'll try this. I'll try 33 and 32. Because I think my book's got things around the wrong way. A 17. 17's the one I want. It is. I was right. 17 and 16. And you. All the way down here. Alright. I think I've worked out my math. That works. I like that. Very, very, very good. So, what's the timing we got? Let's do one little bit more, shall we? That's the sound. Playing a song. Okay. Creating sound effects. We'll do this one last little... we've got 1 and a bit pages left for music. Okay, let's make it a really long one because I'm on a roll, so let's go for it. Shall we? Why not? So, creating sound effects. Your C64 SID chip lets you create a wide variety of sound effects, such as an explosion during a game or a buzzer that warns you that you've made a mistake. Here are just a few suggestions for creating sound effects. Vary rapidly between 2 notes to create a tremor sound. Using the multi-voice effects to play more than one voice at a time, with each voice independently controlled, so you have different noises at once. Or use one voice as an echo or response to another voice. Use the different pulse widths to create different sounds. Use the noise waveform to make white noise to accent tonal sound effects. Create explosion noises, gunshots, footsteps, or alarms. When you use the noise waveform with the same musical note that create music, you can create different types of white noise. Combine several high-low frequencies in rapid succession across different octaves. Try poking the extra note settings in Appendix M. Here we have some sample sound effect programs. The Commodore 64 Programmer's Reference Guide contains more examples, as well as more information on creating sound effects. So, just so you see what I'm about to type, it's just this little, I just read from here to there, and this is our little program we're going to read. So, you can pause that if you wish and see what's there. And I think that's the whole program. Yep, that's it. The next one is a shooting sound. So, let's get back to the Commodore. There we go. So it's a doll crying. So, new. Clear the SID chip. 5. 4L equals 54272. I've already memorized that number for some reason. And 54296. Poke L 0 and just next, just clear itself up. Okay. Next one. I do have to say though that back when I was doing this stuff on my Commodore using this exact manual, I mean this exact physical book here, I spent most of my time playing around with the sounds here, which is quite nice, I have to admit. So S equals 54272. Poke. They must have got different people to write different things at different times, because now this thing has multiple things attached to it. So, okay, poke 54275 with 15. Poke, because there's different coding styles for different each of these programs for some reason. And 54274, setting the attack and decay, I think. Attack, decay, and sustain release thingy. I think that's what that line does, and sets the starting point for the SID chip. Okay, 20. I do have to admit, the SID chip sounds really cool. It really rolls off the tongue, doesn't it? Even though it stands for a very bland thing, acronym, a sound interface device. But SID just sounds better. Sounds nice. Poke. S. S. Oops. Really fucked up. S. Plus 465. So these last two lines are just done. One sets the volume. This one turns on the pulse waveform for voice and just turns it on. Thankfully, in this tiny little program, there is no data lines, so that's nice. So no manual stuff like that. Poke. S. Plus 5. Put 15 in there. That sets the attack and decay. Now we play our note. And this one does the release time. Okay. 4. Oop. Don't forget your line numbers. 50. 4x equals 200 to 50. So it's going backwards to 5, not 50. 5. Step minus 2. So it's going down in 2 lots. I don't know. It's going like twice as fast or something. Okay, 60. Poke. S. Plus 140. Now I do remember this program, and the sound it's about to make is really hard on the ears, so to speak. And that last line was just set the high-low frequencies. Now we go 70. Poke. Is it 70? What was just doing? No, 70. Poke. 70. No, 70. Oh, 4. It's a 4. Idiot. 4 x equals 150 to 5 step minus 2. So going backwards again. Why? I don't know. They never really explained it, I don't think. But poke S plus 1 with 40. And that sets some different high-low frequencies. Poke S with X. And next. 90. Poke S plus 4. Comma 1. So that line turns it off. So it's just going to make a tiny little sound effect and then end it. So what I would like to Well, we'll run this. Run. That sounds different than what I was expecting. That sounds weird. That's not exactly what I was expecting. There's nothing wrong with it. Let's run it again. It's supposed to be a doll crying. Hold on, maybe it's the wrong SID chip. Hold on. Let's try this one. Alright, well, that was a bit of a bust, I have to admit. But let's do our next one, shall we? Let's do another one. Okay. This next sound effect, I'll just show you. Please excuse the grubbiness of the book. Is a shooting one. Then we get on to some filtering down the bottom here. So, alright. It's just this sound effect one looks like a lot of just peeks and pokes. So let's clear up our, well, first of all, put it back onto me. Let's clear up our basic memory. New. And let's start, shall we? 5. Let's do, oh, this thing again. 4L equals 54272 54296 poke L, comma 0 next. 10. So the start of the S of the SID chip is that. So 54272. 24 x equals 1520 step minus 1. So it's gone backwards again. What? So it sets up a volume loop. Okay. So what's the next one? It is 30 poke S. So plus 24 X. Okay, so it's gone from 15 down. So you get a hairy loud noise and goes down in volume. 40 poke S. Plus 4 129. That sets it up as a noise waveform. Okay. 50 poke S plus 5 comma 15. 60 poke S plus 140. So that sets the high frequency. And I screwed this up again. Plus, what's it, 1? Yep. Sets the high frequency to 40. 70. Poke S. Poke S. Oh, that's what it is. Okay. goes next. Oh, okay. So it goes bang, and then lets the volume drop to 0, then just stops. So it's everything back down. And go 80. Poke S plus 4 128. So what you would do, you would have this tiny little program as a little function subroutine of something else at some point. So you can just call on it when there's a collision detected or something like that. This is the detect delay, back down. So essentially cleaning up after itself. 100. Go to, whoop, did it again. Go to 20. So that just loops itself over and over. This one should work pretty much out of the box. So let's see. I timed that one beautifully in the stop. Timed it right at the point where it was still going. Still going. Yep, there it goes. Okay, cool. So that's the sound effect. Let's poke it with the stick, shall we? Let's change the upper frequency a bit. Let's change you to, say, I don't know, 169. Let's see if that works. Run. Well, it certainly changed the tone of it, which is nice. So, there we are. That's what you do. That's how you do it. You set your high and low frequencies, or the pulse width. No, well, when you're using the square waveform, you also have, in addition to the pulse width, so if you're using the pulse wave set, you have to set that as well, including the high and low frequencies. Set your waveform, set your attack, decay, and sustain and release values. It has its own same defaults, I think. And simply set them, when you set the frequencies, you turn it on and away you go. When you set your waveform also. So you set your frequencies first and then set your waveform and turn it on. Let it go for a little bit, then turn it off again. So essentially you're doing fiddling with some knobs, press a button, turn it off, fiddle some more, press the button, fiddle some more, press the button. So that's how it works. So that's how we do it. That's pretty cool. That's a nice way of doing it, I guess. So that's cool. Alright, so let's get on to the next bit, shall we? Okay. Sometimes a certain waveform may not be quite... Well, hang on. Let's explain the actual program we just done first. Sorry. The loop that begins at line 20 sets up fading volume so that the sound of the gunshot starts at high volume, 15, and fades to 0 as the loop executes. Press the run stop key to end this program. As we've said before, the best way to learn a new area of programming is to experiment, which we just did. So anyway, let's get back. The next bit, filtering. Sometimes a certain waveform may not be quite the timbre I can never pronounce that word properly. Timbre you may require. For example, it would be difficult to imagine any of the preset waveforms in the SID chip sounding anything like a trumpet. To give you additional control over the sound parameters, the SID chip is equipped with 3 filters. A high-pass filter, this filter reduces the level of frequencies below the specified cutoff frequency. It passes all the frequencies that are at or above the cutoff while cutting down the frequencies below the cutoff. A low pass frequency. As the name implies, this filter passes the frequencies below the cutoff and reduces the level of those above. A band pass filter. This filter passes a narrow band of frequencies around the cutoff and cuts down the level of all others. An extra filter called the notch reject filter can be synchronized by combining the high and low pass filters. This passes frequencies away from the cutoff while reducing the level at the cutoff frequency. Register 24 determines the filter type you want to use. Remember that this is also the register used for the volume control. The following bits are used for filters: bit 4, 5, and 6. A filter is activated by setting the relevant bit in register 24. You may not wish to filter all voices at the same time. Register 23 determines which voices are to be filtered. The bits are as following. Bit 7 to 4 doesn't make any sense. 7 to 4, filter resonance 0 to 15. 3, filter external input. 2, filter voice 3, 1, filter voice 2, 0, filter voice 1. When a specific bit is set, the output of the voice can be diverted through the filter. The cutoff frequency is an 11-bit number. The upper 8 bits, 13 to 3, are stored in register 22, while the lower 3 bits, 0 to 1, are stored in register 21. This gives you a range of values between 0 and 2047. Try adding the following lines to the example program to filter the voice and hear the difference in sound. We will be using a low pass filter which will allow only the lower components of the sounds to be heard. Alright, so let's do this then. So, in case you're wondering, I just read a lot of it, so I'm not going to show you right now. So what we're going to add, hold on, I will show you this. So we'll go to me. I am going to be adding these lines here to the thing we just looked at. See up here, here's your filter bits for what it is, and down here as well. So this one. Okay, so let's put it in, shall we? Alright, 30. Whoop, wrong window. Here we are. Still recording? Yep, still recording. So 30. Poke S plus 24 with 31. So we go remark full volume plus low pass filter okay, and 35 poke S plus 23 with 1 remark, whoops, forgot everything is capitals. Right. Select filter for voice 1. Okay, one more. 37. Poke S plus 22 and put 128 in there. Then we go. Then another one we poke S21 7 and remark select cut off frequency. Okay, so if we do a list, let's have a look. So now we have the filtering, the low pass filtering. And for that, we filter, okay. So let's run. And 37. What did I do wrong? S plus, there's supposed to be a plus there. Oh. I won't do that remark. 21. I'm sure someone probably screaming at me right now. Oh, I did not make that mistake. Alright. So list. See what we get. Alright. Run. Okay, that does sound a bit different. It sounds more like a TV. Well, okay. Try experimenting with filters. Filtering a sound as it passes through the ADSR phases of its life can produce interesting effects. For further information on how to use the Z chip, consult the Commodore 64 Programmer's Reference Guide. Music Composer. The Commodore Music Composer cartridge allows you to compose music on your Commodore 64 without having to concern yourself with the workings of the Z chip. Excuse me. Facilities are provided to allow you to type in program lines that consist purely of special control characters. This enables you to play any combination of sounds that you require using all the features of the Z chip. Once you have composed your masterpiece, you can save it on tape and then play it back at your leisure. While the music is playing, a music stave scrolls across the screen displaying the notes that are being played. This allows you to get the most from your Z chip with minimal effort. And with that, that is the last bit. There's a little bit here on advanced data handling, but these are just basically how to use arrays or anything else, or tables. So if you'd like me to do that, please comment saying, yeah, it's a very tiny chapter and all this, but and basically more advanced usage of the read functions. Yeah. Alright. Alright. So, what a series, I guess. I'm a little bit sad to see it go. It's actually been really cool working through this book. It's been all the way from the beginning to beginning in basic on this grubby page here, all the way through. It's been great, actually. So with this, since this series is now pretty much ended, if you'd like me to work on another machine using BASIC or something like that, please let me know. It would be nice if there was one I can actually get the physical manual for to work through. That would be nice, like doing an old Sinclair machine, to work my way through that, because those ones are a lot harder to work with than the Commodores. But anyway, thank you very, very much for watching. I hope you learned something. And if you have, please post it on the comments down below if you can. That would be nice. And I'll see you all in another video, I guess. Bye bye.